In this lesson, we're going to be looking at orthogonal trajectories and derivatives of inverse trigonometric functions. First of all, let's look at orthogonal trajectories. Graph below is the equation of x times y equals c, where c is a constant. So this gives us a family of curves. C could be positive or negative. So we would have an infinite number of curves. I've just drawn a few here for us. And then we're also going to graph x squared minus y squared equals k. And we're going to overlay it on top of x, y equals c. So these graphs are called orthogonal trajectories. The reason that they are called orthogonal trajectories is that if we looked at a point of intersection, say this point here, and I drew the tangent line to the red graph, and I draw the tangent line to the white graph, the tangent lines intersect at a 90-degree angle. So if we have two graphs at the point of intersection intersecting with perpendicular lines, which means they intersect at a right angle, they are considered orthogonal trajectories. Show how these graphs are orthogonal trajectories of each other. Now, thinking through this process before we get started, if we want to show that these two equations are orthogonal trajectories, we would need to show that the slope of the tangent lines are perpendicular to one another. Well, that would indicate we need to find the derivative of each one of these equations and compare them. Are they negative reciprocals of one another? So let's start out with x times y equals c. Let's find the derivative, and we're going to use implicit differentiation. Using implicit differentiation, we'd have the first times the derivative of the second plus the second times the derivative of the first. We're applying the product rule, equals the derivative of c. C is just some number, so that equals 0. Solving for y prime, we would get y prime equals negative y divided by x. Let's do the same for the other equation, x squared minus y squared equals k. Finding the derivative implicitly, we get 2x minus 2y times y prime equals 0. K is just some constant. Solving for y prime, we get y prime equals x divided by y. We can see that these two are negative reciprocals of one another. These represent the slope of the tangent lines for these two equations. Therefore, the slope of the tangent lines are negative reciprocals, so these would be orthogonal trajectories. Moving to derivatives of inverse trigonometric functions. We can use implicit differentiation to find the derivatives of inverse trig functions. Now, let's just do a little bit of review from trigonometry. If we have the equation y equals sine of x, and we're looking at the inverse of this function, if I want to find the inverse of some function, let's just take a simple function, y equals 3x squared minus 1. If I want to find the inverse, we know that we switch the x and the y, and then we would solve for y. This is the inverse of this function here. Just simply by switching x and y, you have found the inverse. Even though we haven't solved for y, it is still the inverse. Keeping that in mind, let's apply that to our sine function. If we simply switched x and y, this is the inverse of y equals sine of x. X equals sine of y. That's the inverse. Now to solve for y, we have agreed upon a notation. We said, well, we're going to create this notation so that we can solve for y. These are equivalent equations. They mean the same thing. They're both representing the inverse of y equals sine of x. That's very important in the understanding when we go through and find the derivative of our inverse trig functions. We need to understand that x equals sine of y is an equivalent equation to y equals sine inverse of x. Now, y equals the sine of x means the sine of an angle equals some number. But when we're looking at the inverse, the inputs for the inverse would mean the sine of some number equals an angle. And we just discussed that these two equations for the inverse are equivalent. And then we have this restriction for the sine inverse. If we just did a little bit of a review from our trig class, if we were to graph y equals the sine of x, we know that looks like this. And I put a little break in the graph because I'm going to be erasing part of the graph, and I don't want to erase the whole thing. But there wouldn't be those breaks in the graph. Now this is the sine graph, the sine function. We can see this is not one-to-one. If we drew a horizontal line through this function, it would touch it more than once. Therefore, it's not one-to-one. Therefore, the inverse would not be a function. Now, that doesn't mean the sine graph itself doesn't have an inverse. Actually, if we drew the inverse, it would look something probably like this. Now, this is not a function. You can see it doesn't pass the vertical line test. Therefore, we're going to restrict the domain from pi by 2 to negative pi by 2. Now when we graph the inverse, it will be a function. Now remember, when we graph an inverse, we switch the x and the y's. So if I switch the x and the y's, well, whatever's on the x-axis over here for y equals sine of x now is going to be on the y-axis. And we know that the max and min value for the sine is 1 to negative 1, or negative 1 to 1. So those now are going to be on our x-axis. And thinking about inverses graphically, to find an inverse, if you graph the function, if you reflect that over the line y equals x, that's how you can draw the inverse function. So if I drew that by reflecting, there would be the graph of y equals the sine inverse of x. So there's a little bit of a review about the sine inverse. Now remember, the sine inverse of x can be written this way also. These mean the same thing. So we're going to now try to find the derivative of the sine inverse of x. Now to do that, we're going to go back to this form, x equals the sine of y. We're going to use that form to find the derivative of the inverse function. Let's take the derivative of x equals sine of y, and we're going to take the derivative implicitly. So if we take the derivative of x is 1. Derivative of cosine of y, the derivative of sine of y would be cosine of y times y prime, because we're taking the derivative with respect to x. And then if we solve for y prime, we'd have 1 all over cosine of y. That's the derivative of the sine inverse, but we want this as a function of x. We're looking for the derivative of this, so it should be a function of x. Let's build a triangle with this being angle y. I'm building a 90-degree triangle here. And let's use this piece of information right here where it says the sine of y equals x. Well, if this is angle y here, the sine of that angle is opposite over hypotenuse. So I could write it as this x equals the sine of y, but x would just be over 1. We know the sine of angle y would be the opposite. So here's the opposite side. That would be x. The hypotenuse would be 1. And now we can find the adjacent side. The adjacent side would simply be 1 squared minus x squared. And the reason that we're doing this is now we can find the cosine of this angle y in terms of x. So looking at the cosine of angle y, we know the cosine is the adjacent over the hypotenuse. So the adjacent is 1 minus x squared over the hypotenuse. So now coming back over here, we can replace cosine of y with the square root of 1 minus x squared over 1, but I don't need to write that. And there is the derivative of the sine inverse, or arc sine. Some books you may have seen in your trig class where it's written as the arc sine of x. That's the same thing as the sine inverse. So there's the derivative of y equals sine inverse of x. So let's just write the derivative. I'm going to have to do it over here. The derivative of the sine inverse of x we just found to be 1 over the square root of 1 minus x squared. That's our derivative. Another example, find the derivative of the tangent inverse of x. Now you could go through the same process that we just did with the sine inverse. So we're going to rewrite tangent inverse of x in its equivalent form, x equals the tangent of y, and then take the derivative implicitly. It would be a good idea for you to stop the video and just give this a try. Try to find the derivative of tangent inverse. We would find the derivative implicitly. So we take the derivative of both sides. The derivative of x would just be 1. Now the derivative of the tangent of y would be secant squared y times y prime, or dy dx. Solving for dy dx, we have 1 over secant squared y equals dy dx. Now there are two different ways we could go about finishing this problem. We could use the technique that we just saw in the last slide. We could build a right triangle, And we could say this is angle y, and go back to this relationship, and we know the tangent of an angle is the opposite over the adjacent. Therefore, the hypotenuse would be 1 squared plus x squared. And then we could go back to our triangle and say, well, we need the secant of angle y. And the secant of an angle, which is the reciprocal of the cosine, would be the hypotenuse over the adjacent. So there's the secant of angle y. But we need, down here, we need secant squared. So if we squared both sides, we would just end up with 1 plus x squared. And we know this means the same thing as secant y squared. And therefore, we could go back to here and replace secant of y now with 1 plus x squared. And that would be our derivative. So there's method 1. The second method that we could have used, if we remembered the Pythagorean identity, one plus tangent squared y equals secant squared y. We then could have made the replacement back over here. Secant squared y, this was the result from method 1. So here's method 2. We could have replaced secant squared y with 1 plus tangent squared y. That would be our dy dx, but we want it all as a function of x. And then if we go back up here and look at this relationship, we could say if we squared both sides, we could find tangent squared y equals x squared, and then make that replacement here to get 1 plus x squared. And you see we get the same result. So there's the derivative of the tangent inverse of x. We found the derivative to be 1 all over 1 plus x squared. So there again is showing the two different methods.